Hi guys, and welcome to this third tutorial looking at the MBA combined data. For today's tutorial, you'll want to open the interpretation and visualization workbooks and also have the script open in SAS. Now, if we look at where we're at the moment, last time we showed that the seasonal estimates for the mixed model had much greater confidence intervals than for the two-way ANOVA or for the one-way ANOVA. And I suggested that that was to do with the random effects that we use within the mixed model. So what I'm going to do now is I'm going to talk you through the difference between fixed and random effects. And it's important to note from the outset that both of the fixed and random effects account for variance or error within the model. They just do it in different ways. So whereas fixed removes that variance, as shown by the covariance parameters, random effects just partition it. And partitioning the variance in this way can be really useful when either the effect is not the one that we are looking for to primarily compare, or when any of the data that we have actually violates the assumptions of normality. For example, when there is clustering within the data, which means that it's not independent, or when missing data is there, so we need to account for the missing data to understand the trend of a given group. So just to reiterate, fixed effects work with the means and give these mean estimates, whereas random effects work with variances, which we can square root to standard deviations. And in square rooting the standard deviations, we can then start to understand the variability within the data. So if we move over to SAS and run both the two-way ANOVA, which starts on line 65, and the mixed model, which ends on line 171, we can start to look at these differences. And one of the key differences to look at is the degrees of freedom. Now, because fixed effects work with means, they consider every data point to be fixed. That is, every individual data point matters. On the other hand, random effects consider them to be random, and as long as we can work out more or less where they're going to be or the probability of them belonging to a group, they can be anything. So whether it changes by 1 centimetre or 2 centimetres does not necessarily matter, whereas that can have a big effect on the mean, which is why those figures are kept fixed. And this shows itself in the degrees of freedom that the model uses. So you can see when you look at the estimates for the positions and for the seasons, which we'll look at in the least square means, you can see that the degrees of freedom are 483 all the way through. And this is, as I say, because these are fixed observations. On the other hand, when we look at the estimates in the mixed model, we can see that the degrees of freedom for the positions is only 8. And this is because we only calculate the variance as a fixed element. And with using the variance, what we could then say is there is a certain area around the intercept for that position where all of their data should be. So all of those observations should fall within that. And that allows us to account for missing data because we just know that the missing data should be somewhere within that element. And it allows us to account for clustering because we're saying that all of these variables belong to this group. Now, it does have a slightly negative effect with regards to your certainty in the model. So if we look at the individual estimates for sensors from the ANOVA and the mixed model, it's difficult to see, but the confidence intervals are slightly greater for the position within the mixed model, which is a triangle, compared to the two-way ANOVA, which is a diamond. And that's because we need to account for any observations which could happen. So we need to give a little bit less certainty because we don't know if the next person is going to be a greater or less have a greater or less jump height than the mean or even the confidence intervals that we've got from the fixed effect. And this uncertainty carries through to the season estimate and can have a big impact on the differences that you actually see. So although we can account for clustering and missing data through the random effects, they do lead to less certainty within the model. And alongside that, there is another element in terms of how they change what happens with the model. If we just ignore the means for now and focus on the intercepts, if we compare the positional mean from the ANOVA to the intercept from the mixed model, we can see that they're different. So the mixed model is the thick line and the ANOVA is a dotted line. And you can see that the mixed model has moved the intercept of the center closer to the grand mean intercept. If we look at this with a couple of other positions, we see a similar trend. So if we'll stick with the three that we were working with before, so here's the small forwards. And you can see that the trend is now, the difference is much, much less, but there is still, you can still clearly see the dotted line of the ANOVA. It's not completely overlapped with the mixed model intercept. And then finally, you guys can look through all of these on your own. They're all here for you to have a look through for all of the other positions, but we're just going to look at three here. And you can see again, this is even less of a difference, but you can just about see the dotted line above the mixed model intercept for the shooting guards. And this is important because what mixed models do is they shrink intercepts towards the mean. They say, right, we know this is the mean intercept, the black line. Now, show me how much your data says we should move away from that. And in the case of centers, it results in quite a large difference, a reasonably large difference between the position estimate and the position estimate for the two-way ANOVA and the intercept for the mixed model. And that's because it's not as influenced by this really big outlying number as the positional mean is. And so this allows the model to be more certain in where the groups are or how close to the mean the groups are, and keeps them fixed within that kind of like variance and standard deviation. And if we look through all of the intercepts, so take the shooting guard out and include all of the intercepts, you can see how all of the intercepts are grouped around this mean number. Now, if you open the interpretation spreadsheet and go to the CovTest worksheet, this between position variance represented by the intercept with the subject's position, this variance here represents the difference between these lines and the grand mean intercept, the black line. We then have the within position variance, which is the difference between each individual estimate and all the points for that position. So the within participant variance is now the difference between these points and this estimate, because we have the season as a fixed effect within the model. If we didn't have season as a fixed effect within the model, it'd be the difference between these points and this line. And it's easy to see from the two images that we've just seen how the within position variance particularly for sensors, is much greater than the between position variance. And just in case you missed it, I will add all of the intercepts from the mixed model now. And look at that, these are all really nicely grouped around this mean line, whereas you've got quite a big differences from the individual estimates within position for center. And so your within position variance is the residual in this situation. And hopefully you can see that the within position variance is actually the same as just the residual in the two-way ANOVA, which has very little meaning. On the other hand, within the linear mixed model, now we've partitioned, we can see that the amount of variance that we've taken out is now related to the positions. And in the next video, we'll show you how to interpret that even more. But hopefully this video has given you an understanding of why mixed models can be much more powerful than using two-way ANOVAs in the same situation.